This is the calendar for today, Thursday, December 10th. Good grief, Christmas is almost, this is right around the corner. You're going to need your calculator. Please have that at your side, as I told you yesterday, or Tuesday. Also, we're going to do some practice calculations. We are not going to get to this lab. The lab is, we won't get through these notes. I left 2 sections of Chapter 5 hanging. We're going to finish up the section 5.3, and then we're going to go back to the first section of the chapter and talk about quantum numbers. Like, what? So hang with me. It'll be really weird stuff, but hopefully by the end of, well, by next week, it will make some sense. I think. We'll see. Maybe not, but hopefully. So don't worry about the virtual lab. We'll start that tomorrow. This worksheet, or note sheet, see, people keep turning them in. I've told you guys, don't turn them in. Oh, let me go back one more thing on the calendar, my bad. I have been having an issue where I caught 3 sets of people with really blatant sharing is not caring, borrowing, cheating, and taking material from another student, whether it's given willingly or not, and presenting that as your own will earn you and the person you got the work from a 0 on the assignment. So please don't do that. Please do your own work. There will be an exit ticket showing up before before you leave today. Okay, so this is the worksheet that we were, not worksheet, note sheet that you could use or not to take your notes on Tuesday. And we got introduced to Max Planck and his formula for energy. Planck's constant, 6.6262 times 10 to minus 34th joules times seconds. We'd already learned about the wave equation, so we're going to learn how to calculate energy if we know the wavelength of the light. Okay? I did examples for you last week, last Tuesday, not last week, still this week. But I want you to do some for me now. Okay, so I'm going to get to the right place. There we go. And I'm going to ask you, well, refresh a couple of things for you from Tuesday. So again, if you have your calculator, you might be able to earn some hero points. So solving the wave equation for frequency is pretty straightforward. You have to remember what the variables mean. Lambda, this upside down Y looking thing, is length of the wave. Nu, it looks like a V, it's not, is the frequency. And then C is the speed of light. That's a number that you need to have, 3.00 times 10 to the 8 meters per second. If we measure the wavelength in the lab, we can substitute that, divide the speed of light by the wavelength to get the frequency. Planck's equation is E for energy, H is his constant, 6.6262 times 10 minus 34. Since the frequency is the speed of light divided by the wavelength, you can just substitute that into Planck's equation. The next thing that you do is you put the 6.6262 in place of the H, 3.00 times 10 to the 8th, divided by whatever the wavelength is that you measured, and you will get the energy for that particular color of light. So I actually might not have gotten through this with this class, huh? The 2 equations, the 2 constants, are things that you need to have at your fingertips, if you will. So if I tell you there's 1.00 times 10 to the minus second meters, that's the wavelength of a microwave. Divide speed of light by that value, you get the frequency. Multiply the frequency by Planck's constant, and you get the energy. Same process, take the wavelength, divide it into the speed of light, and you'll get the frequency. Take the frequency and multiply it by Planck's constant, and you'll get the energy. Show you guys these tomorrow. All right, so here's what we're going to do. We're going to use those two equations. I don't have the constant values listed on the slide, but hopefully you have them written down somewhere from Tuesday. This is a representation of the three different subdivisions or categories of ultraviolet radiation. There's a range, 100 to 280, 280 to 315, 315 to 400. UVA, remember, gets all the way down to the ground and all the way through your skin. Okay. UVB, most of it gets blocked by the ozone, but some of it damages your epidermis, and UVC gets totally blocked by ozone. If we use the shortest value for the wavelength for each of these subdivisions of ultraviolet radiation, we can calculate their frequency. However, the problem with this particular slide is that it's in nanometers. Nanometers, nano is the prefix for billion, 10 to the minus 9. That's a lot. Okay, if I took a meter stick, about from my nose to the end of my finger, if I took a meter stick and chopped it into a billion equal pieces, that would be a nanometer. That would be really hard to do. A meter stick has centimeters marked and has millimeters marked. Centimeters are hundredths, millimeters are thousandths. So billionths is a big difference. So 100 nanometers, if we change 100 to scientific notation, that's 1. You don't get to keep any more sig figs because there's only 1 sig fig in that number. There's no decimal, so those zeros aren't significant. 1 times 10 times 10, which of course is 1 times 10 to the second, would be the length in meters. So that's one thing you have to be really careful about is units. Okay, this is reporting in nanometers, but to do the calculations, you need the wavelength in meters for these two formulas and constants that I gave you. Right, 280. Again, no decimal here. This little tilde thing is means approximately from about 280 to about 315 is the representation. Different scales break it slightly differently. So 2.8 times 10 times 10, or 2.8 times 10 to the second. Multiply that by 10 to the minus 9th. Remember, when you multiply exponents, you add them, right? This math stuff. So positive 2, negative 9 makes a negative 7. And then this last value for UVA, no zeros, doesn't have to have a decimal. All three of those are significant. So we need to have all of them in our answer. 3.15 times 10 times 10. 3.15 times 10 to the second. 10 to the second times 10 to the minus 9th is 10 to the minus 7. So now we've got all our wavelengths in the correct unit. I won't be that tricky with you. I'll give you the wavelength in meters. I just wanted to point that out. All right. Oops, sorry. So the next thing we need to do is take that wavelength, boom, and divide it into the speed of light. And no one came to my office hours yesterday, so I'm assuming everybody knows how to use their calculators and has no problem doing that. Maybe. Speed of light, again, 3.00. My calculator, I use the second and the EE, which is the comma button, which is over the 7. My display now has a big capital E in it. That's not for energy. That's supposed to mean there's the exponent for base 10. Okay, so 3.00 times 10 to the 8th. Notice I didn't hit the times button. I didn't hit the 1 or the 0. Okay, and then I'm going to divide that, hit the division button, by 1 second EE, and then plus minus, or minus in parentheses, not the subtraction button, 7.
Just divided by what? By 7?
1
Oh, okay.
times 10 to the minus 7. Okay? And you should get 3 times 10 to the 15th. What you'll actually see probably is a whole bunch of zeros after the 3. You don't get to keep them. Okay? This has 1 sig fig. Your answer gets 1 sig fig. The number of digits in the coefficient have to correspond to the significant digits. Same process. So this is per seconds, right? So I'm taking speed of light in meters per second divided by meters per second divided by meter, gives you per seconds as the leftover unit, which is hertz, cycles per second, waves per second. Okay, we're going to do the same thing, 3.00 second EE, or however you do it on your calculator. Positive 8, you don't have to put in the positive, it's just 8. So you should have 3.00 E8 if you have a TI-84. You might just have a gap between the coefficient and the exponent. You might be lucky and have a little times 10. Just depends on your calculator. Okay, I'm going to hit divide. This time I'm going to divide that number by 2.8 times 10 second E to negative 7. Oops, yeah, I hit the right button. All right. You'll notice that you get a string of numbers. I don't know if you guys can see this or not. I hope you can. You'll get 1.071429 E15. That looks really impressive. Do not write them all down. You're not allowed to have all those digits. Okay? 3.00 is 3 sig figs. 2.8 is 2. You have to round to 2. It does not become 1.0. It becomes 1.1 times 10 to the 15th. That's 7, bumps up the 0 to a 1. All right, everybody try this one for me, and I'll give you hero points, right? Here's the wavelength. Speed of light again. 3.00 second is 8. Divided by 3.15. What do you get? Type it in the chat or unmute if you like. Do I have I'm a robot having a seizure? Am I okay? Or is it still glitchy?
It's a little better, and I can kind of hear what you're saying. I just have to really focus.
All right. I apologize. I will talk louder. All right. Anybody got an answer yet?
I'm not sure, but is it 9.52 times 10 to the 15th?
It is not the 15th, but you're really warm.
Okay.
Anybody else? Jack gets a hero point. Anybody else?
Mine is the same, but it's to the 14th.
14th. Who is that?
Bethany.
All right. That is the correct response. 9.52 times 10 to the 14th is what you should have for your answer. Whoop. Not that one yet. Ah! I got too many things open. Hang on. Hang on. It's here somewhere. There it is. All right, so you should have gotten 9.52381, depending on how many spaces your calculator wants to give you, and times 10 to the 14. That is the correct response. All right, so these are wavelengths on the top in the orange. These are frequencies in the yellow. Next thing we need to do is take that frequency we just calculated and plug it into the energy equation. Again, 6.6262 times 10 to the minus 34. Okay, so for your calculator, 6.6262 second e negative 34. What? Okay, that's the start. Then hit times, and we're going to do 3 second e 15. Again, both of these numbers only have one sig fig. So when you look at your calculator display and it says 1.9878886, you don't get all of those. Okay, you have to round it. And I mean, honestly, that's what they do in stores all the time. It's not $2, it's $1.98. It's $2. Okay, so you round to 2. And the exponent says negative 18, so you are supposed to put in times 10 to the negative 18. This time it is in joules, because remember Planck's constant is joules times seconds. Seconds on top cancels the second per second, which would be second in the denominator. Okay. Let's try one more, and then I'll have you do the third one. 6.6262. Second e minus 34. Times 1.1 second e 15. I'm going to tell you that the answer I'm going to show you is slightly wrong. Chime in and tell me what the right answer should be when you get there. Oops. And hopefully you guys got it. What is wrong with my answer? Anybody? What should the coefficient be? I had 7.2. What should the coefficient be?
Should it be 7.3?
It should. Good job, sorry. Thank you. So your calculator is going to tell you sorry, I got to get it back in here. 7.2888. That can only have 2 sig figs, so it should be 7.3. And right, so it's incorrect on here, but it should be 7.3. Right, last one. This one's also slightly incorrect. Chime in when you think you get the right answer. Or type it in the chat. Okay, well, I'll leave you hanging then. It's close, it's really close, but there's 1 digit off in the coefficient. All right, let's finish this up. So just a hint, there's 3 sig figs, 3 sig figs. This should have 3 sig figs. All right, the last little bit on Tuesday's note sheet, just wanted to run through skim the surface of quantum mechanics. So classical mechanics is the set of equations and laws and stuff that Newton came up with to describe large macroscopic objects, whether it's people, cars, planes, rockets, planets. It works really well for big stuff. Niels Bohr on the right is the one that came up with the concept of what we call quantum mechanics, the quantum mechanical model. He didn't finalize it, he got us on the right path. And that was from his work looking at the hydrogen atom. Physics has kind of 4 quadrants to it. There's a lot of subdivisions within each of them. Classical mechanics, that's pretty much all any of us have to worry about, because quantum mechanics takes care of itself. But big things to really the smallest things, parts of atoms. Moving slow, moving at the speed of sound or close to it as you go along. So out here, quantum mechanics is dealing with atoms and basically at the speed of light. These other 2 categories we don't have to worry about. But what quantum mechanics does is describe how subatomic particles and inside of and as atoms as well act like they're waves. So remember, there's matter and energy, particles and waves. At the big level, no problem discerning. At the subatomic level, they start to look the same. Is basically what that means. Some of this stuff was first worked out by the guy that came up, whose last name is used for our frequency unit, Heinrich Hertz, along with a bunch of people, including J.J. Thomson, was dealing with light and metals and noticing that if you strike materials with a certain kind of light, something comes off of it. And what he did is he did a lot of measurements. He didn't put it all together, I don't believe, but he did work, this is just an example, potassium, which is a metal. And if you hit it with 700 nanometers, the longest red wavelength of light that your eyeballs can discern, it has a certain amount of energy. And it's not enough energy to knock any electrons off. Of course, at this time, they didn't call them electrons. They didn't even, hadn't discovered them. That was what Thomson did, remember that. On the other hand, if he hit it with a shorter wavelength of light, green light, something came flying off at a pretty good clip. And if he hit it with a purple wavelength of light, 400 nanometers, the shortest wavelength that your eyeballs can see, that something, these somethings came off at an even faster clip. Okay, so he documented and studied what we now call the photo, or photons of light, electric effect, the electrical voltage kind of stuff. So if you give it enough of a push, you can knock electrons off. Einstein, while he was working at the patent office, he did a lot of math craziness. And one of his numerous 1905 papers, he had studied Heinrich's work, apparently, and he mathematically explained what was going on with the term quanta. Okay, quantum. We call bundles of energy moving at the speed of light in waves, as we call them photons. But he, at that time, it was called quanta, which is for the quantum. He got the Nobel Prize for his work, his papers in 1921. He explained that data by basically saying light acted like particles and light acted like energy. It had waves. Again, we call light quanta, plural for quantum, photons, or use that information and put it forward that these colors of light that you see in the spectral lines had something to do with the electrons and their energy. And then this is about the time when de Broglie put together his wave-particle duality. Matter can be like waves, and waves can be like matter. And of course, we use electrons now to study things with electron microscopes. Actually, it's been around for quite a while. Electrons move at different speeds. They have wave-like properties, which allows them to get in between the nooks and crannies, if you will, of the dust mite. And then that can get transferred to a computer. The image has been colorized, just so you know. But all this detail we would not be able to see with a regular lens. So the electrons can get in there and show us all of that. So cool stuff. We don't need to talk any more about it because quantum mechanics is now physics. So you have a note sheet, another note sheet, has a periodic table at the top, and then some stuff that looks really bizarre we'll talk about. So, sorry, we left off, oh, you got to see the punchline, sorry. We left off with the concept that electrons live in clouds, and they're not in a set path. My earrings are false. Any picture probably you've seen of electrons circling the nucleus, absolutely incorrect. Okay? I just want to talk to you about the periodic table briefly, and hopefully some of you will start making connections in the next couple of days. It may not happen at all. I made it through 3 years with Chem at Davis without understanding this. I didn't understand it until I had to teach it. Classic, right? So I just want to show you a few things. How do we read the periodic table? You start at the top, just like a book. You start at the top of the page. You start on the left side, you go to the right side. You start on the left side, you go to the right side. Next line, sodium, to argon, potassium, to krypton, etc. Notice that there's 1, 2, 3, 4, 5, 6, 7. There's 7 periods, we call them. Okay, kind of, some schools have 7 periods. We don't have 6. I guess we have 0 periods. We have 7. There's something about the 2 elements, and there's also something about why there's this huge gap. Why don't they just put them next to each other? There's a reason for it. Turns out it has to do with electrons, and they didn't even know it when they made the first periodic tables. So 7 periods, and you're probably going, wait on the sketches, there's 2 down at the bottom. Well, those 2 lines, the lanthanides and actinides, actually, this whole thing should be split right here and shoved apart to make room for these 2 rows at the bottom. And again, it makes a lot of sense when you understand electrons. It's so cool. Okay. All right. Notice something. On the left-hand side, 1, 2 columns. Everybody good with that? On the right-hand side, 1, 2, 3, 4, 5, 6 columns. Okay. You probably learned at some point that the columns have elements that behave the same way chemically. We're going to talk about that a lot more. And maybe sometime you learn their names. We're going to go over those too after Christmas. Okay. So alkali metals, alkaline earth metals, transition metals, etc. Columns are families or groups. Rows are periods. Okay. So 1, 2 column on the left, 6 on the right. Count the middle, the transition metals. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Scandium to zinc. That's 10 elements in the middle. Okay. Down at the bottom. 1, 2, 14. Okay. Lanthanum to terbium, 14 elements. Okay. Hang with me. One more thing I'm going to say, and then hopefully tomorrow it'll start to click a little bit. It won't right now. It's okay. 2 divided by 2 is 1. 6 divided by 2 is 3. 10 divided by 2 is 5. 14 divided by 2 is 7. 1, 3, 5, 7. Huh. Okay. That's all I'm going to say about that right now. Okay. Just kind of think about that. We'll come back to it. There's a silly little flip I want to play for you. You already saw the punchline, but that's okay. Where are the stinking electrons? If they're in these cloud things, where the heck are they? Oh my gosh, that's such an amazing story. I'll make play that for you tomorrow.
You're watching a Nova Science Now video podcast.
If your nucleus, this is kind of silly, isn't it? If your atom's nucleus was the size about of your fist on your Chromebook screen, the closest electrons would be miles away. I'm going to share a couple more things, and then I'll promise we will get out of here on time. All right, so if they're miles away and everything's mostly nothing, where the heck are those electrons? Well, keep in mind that electrons live in those cloud areas where you're most likely to find them, but no guarantee. Okay, right now under lockdown, yeah, most of the time you're supposed to be in your house, but you might not be. Okay, 9 out of 10 times maybe. The proper term for that space is called a cloud, electron cloud, but in everyday talk we usually say orbitals. Some people call them shells also. And here's the kicker. Each orbital contains a maximum of 2 electrons. Okay, so we'll come back to that. How do we find out where electrons are? Well, scientists use an addressing system, if you will, called quantum numbers. And again, keep in mind, it's where you're most likely to find an electron, but you're not guaranteed that it's going to be there. There's 4 quantum numbers. The first one's called the principal quantum number. And on your, like, if you're writing an address on an envelope or something, that would correspond to, say, the state. In the world of atoms, there's only 7 states. There's 7 periods. Okay. The second quantum number is analogous to the city in your address. So in those 7 states, there's 4 cities. In the third part of the address is the third quantum number. It would compare to your street. And then the last one would be like your house number. All right. Hang with me. Just to give you an idea, they're just a way to give an address to the last, well, to the electrons in an atom. All right, make 4 columns really quick. Ready? The quantum number is called, the first one is called principal quantum number. It's abbreviated with a little n. Profoundly, the second quantum number is called the second quantum number, and its abbreviation is L. Third quantum number is M sub L. Fourth quantum number, M sub S. What are they? Okay, well, the first quantum number, or the principal quantum number, those terms get used interchangeably, defines the energy level of the electron. The second one describes something called the sublevel. The third one, the magnetic orientation. And the fourth one is something called spin. So what does that tell us about our electrons cloud? Because that's where the electrons live. That principal quantum number is the energy level. That tells you how big the cloud is. 1 is the smallest, 7 is the biggest. Okay? The size of the cloud is determined by how much energy the electron has. If it has more energy, it can get farther away. And so the distance the electron is, the last electron in this case of the periodic table, but how far away the electron gets to live. Mathematically, this can go from 1 to infinity, but our atoms only have 7 layers. Second quantum number is the sublevel. It describes the shape of the cloud, and we'll see tomorrow that there's some crazy shapes. Okay, there's 4 categories of shapes: S, P, D, and F, and I will show them to you tomorrow. Actually, they're on your note sheet. Third quantum number tells the orientation. So like the compass tells you which way you're going, how to orient yourself in 3-dimensional space. Remember X, Y, Z. Same with the clouds. They can be oriented in different regions around the nucleus. Okay? And then the last one is a spin, and that's something to do with the rotation of the 2 electrons that live in the same orbital. One has to go one way, the other goes the other goes the other way. Okay, plus 1/2, minus 1/2. All of these abbreviations and all these numbers and stuff all fit into Schrodinger's calculations. All right, last thing. Principal quantum number, what is it? It is the energy level. It tells you how far the electron gets to live from the nucleus. It tells you how big the cloud is, and it corresponds to the layers on the periodic table. So hydrogen and helium are in the first, their electrons are in the first energy level. Lithium to neon, their electrons, their last electron is at the second energy level, farther from the nucleus. Sodium, the argon, theirs are in what we call the third energy level, farther and farther and farther away from the nucleus. They also have abbreviations. We won't go into that. Letter abbreviations for those energy levels. Okay, so this probably looks like an onion to you, and that's what it looks like to me as well. So if you imagine that the nucleus is at the center of the onion, and each of these layers, you probably know, get smaller and smaller. Usually on an onion, these are relatively uniform, but that first one's big, and then a little bit smaller. Kind of like an atom. And of course, you know, onions have layers, and so do overs, and so do atoms. All right, that's my silliness for today. There is a exit ticket for you to do. Please do